Close your eyes for a moment and imagine the immense void between the stars. It's not empty. It's occasionally dotted with wandering objects, fragments of distant planetary systems, traveling through the darkness for millions, perhaps billions of years. And every now and then, one of these solitary travelers crosses paths with our solar system, offering us an extraordinary window into worlds we could never visit directly. On July 1st, 2025, telescopes from the Atlas system, Asteroid Terrestrial Impact Last Alert System in Chile, detected a new object moving across the night sky. At first glance, it might have been just another asteroid or comet, something born in the outer regions of our own system. But as astronomers traced its orbit with increasing precision, something extraordinary became clear. This object did not belong to our solar system. It was designated 3I Atlas. The 3I means it is the third confirmed interstellar object to enter our solar system. After 1I, Oumuamua, that mysterious visitor of 2017, and 2I, Borisov, the interstellar comet of 2019. Each of these visitors is invaluable, each a unique opportunity to study matter that formed around another star. The orbit of 3I Atlas is hyperbolic, not a closed ellipse like objects gravitationally bound to the Sun, but an open curve. It came from outside, is passing through our system, and will eventually depart back into interstellar space, never to return. It is a temporary visitor, a one-time passage through our cosmic neighborhood. And, fortunately for us, it won't come dangerously close. Its closest approach to Earth will be about 8 astronomical units, approximately 270 million kilometers. For perspective, that's almost twice the distance between the Earth and the Sun. There is no risk whatsoever to our planet. We can observe it safely, scholars fascinated by a messenger from distant worlds. Estimates based on its brightness and other characteristics suggest that the core of 3I Atlas may be between approximately 440 meters and 6 kilometers in diameter. It is a substantial object, not a tiny particle, but a significant body that survived the interstellar journey. When it was discovered, 3I Atlas was already about 5 astronomical units from the Sun, approximately 670 million kilometers, roughly the distance to Jupiter. It had silently crossed the invisible boundary between interstellar space and our solar system, unannounced until attentive eyes noticed its peculiar movement against the background of fixed stars. Subsequent observations revealed something marvelous. 3. Atlas is not just a cold rock traveling through the void. It has a coma and a tail, unmistakable signs of cometary activity. As it approaches the Sun, solar heat warms its surface, sublimating ice hidden within. Vapor and dust are ejected, forming a tenuous atmosphere around the nucleus and a tail dragged behind it by the solar wind. It is an active comet, glowing softly in reflected sunlight and fluorescence from excited gases. But its composition is peculiar. Spectral analyses of the coma, that temporary atmosphere, detected the presence of metals, including nickel. This is atypical for comets in our solar system. Local comets certainly contain traces of metals, but not in the abundances or forms that appear to be present in 3I Atlas. It's a subtle but significant chemical difference, a clue about the conditions in the distant planetary system where it was born. And they detected water, or more specifically, hydroxyl OH emissions, which are products of the destruction of water molecules by solar radiation. Even when 3I Atlas was still relatively far from the Sun, it was already releasing water vapor. This suggests that it originally had ice inside, preserved throughout its long interstellar journey. It's water from another star system, molecules that condensed around a different star billions of years ago. 3I High Atlas is viewed by astronomers as a messenger from another planetary system, studying its composition, the types of ice it contains, the proportions of different elements in its dust, the chemistry of its gases, can reveal information about the conditions around the star where it formed. It's a form of remote sampling of worlds that we could never reach with spacecraft. And 3I Atlas is not alone. Interstellar objects are not always visible and spectacular comets. Some can be rocky or metallic. Interstellar asteroids, without enough ice to produce a coma or tail when heated. These would be much more difficult to detect, invisible to the naked eye, and challenging even for telescopes, noticed only by their peculiar orbits. The first interstellar object detected was 1I Oumuamua, discovered in October 2017. It was bizarre from the start. It had no observable coma or tail, suggesting it was rocky or metallic rather than icy. Its shape appeared elongated, like a cigar or pancake spinning through space. And it showed a subtle non-gravitational acceleration. Something beyond the simple gravitational pull of the sun was affecting its trajectory. Perhaps outgassing of hidden ice or some other effect. It was so strange that some speculated, half-jokingly, that it might be artificial. Of course, natural explanations are far more likely, but Oumuamua remains enigmatic. The second was 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov in Crimea. It was more composed than Oumuamua, clearly a comet with activity, sublimating ice, and a visible tail. It proved that comets from outside the solar system exist and can be recognized. It was reassuringly familiar, resembling local comets, suggesting that comet formation processes are universal. Every interstellar object has a characteristic hyperbolic trajectory. Their orbits don't close into ellipses around the sun. They come from outside, curve around the sun under its gravity, and then head back into interstellar space. It is this orbital geometry that immediately signals to astronomers, this is not ours, it's a visitor, and they move in fast. The speed at which interstellar objects cross our solar system is usually high, much higher than local asteroids or comets, which are trapped in relatively slow orbits. This excessive speed is another telltale signature of interstellar origin. By studying the material from these visitors, the composition of their ice, the types of dust they eject, the proportions of metals and minerals, astronomers can directly compare the composition of different planetary systems. It's comparative astrochemistry on a galactic scale, revealing whether the building blocks of planets are universal or vary depending on local conditions. The existence of interstellar objects suggests something profound. There must be billions, perhaps trillions, of planetary systems scattered throughout the Milky Way, each occasionally ejecting material into interstellar space. Collisions, close gravitational encounters, planetary migration. All these processes can launch comets and asteroids on escape trajectories. And these ejected objects wander the galaxy for eons, some eventually crossing other systems, like accidental messengers. Some of these objects may have traveled for billions of years to reach our solar system. Imagine a comet ejected when the Milky Way was half its current age, wandering through interstellar darkness for eons, surviving the near-perfect vacuum and cosmic radiation, until finally, by pure chance, it crossed our path. When an interstellar comet approaches the Sun, the sublimation of its ice can create jets, streams of gas and dust ejected from specific locations on its surface. These jets act like small rockets, pushing the comet slightly, causing what is called non-gravitational acceleration. It's a subtle but detectable effect, and it can complicate the precise calculation of its trajectory. Finally, studying these visitors is one of the few ways we have to look inside distant planetary systems without having to travel there. They are windows, samples delivered to our cosmic door, offering insights into how planets and comets form under conditions different from those of our own system. Each visitor is a scientific gift, an opportunity we should not waste. Breathe slowly. Imagine these solitary travelers traversing the void between the stars for millions of years. Keep relaxing. Soon we'll explore more about these messengers from other worlds. Interstellar objects can have dramatic and violent origins. Some may be fragments torn from destroyed planets in other star systems, pieces of worlds that were shattered by catastrophic collisions, tidal forces from nearby stars, or other planetary catastrophes we can scarcely imagine. Each interstellar visitor may carry within its structure the memory of a lost world. Others may be remnants of protoplanetary disks, those clouds of gas and dust that surround young stars and eventually condense into planets, material that never managed to form a world, ejected before it could clump together, now wandering the galaxy as a testament to incomplete planetary births. And the scale is staggering. Scientists estimate that billions of these objects wander through the Milky Way every instant. Not just a rare few, but an immense population. Fragments of countless star systems scattered across hundreds of thousands of light years, each in its own galactic orbit, each with its own silent history. Most of them will never be detected. They are too small, too dark, too distant. Only those that happen to pass relatively close to the Sun and happen to be large enough to reflect or emit detectable light have a chance of being noticed by our telescopes. The 3 we have detected so far are probably just the tip of a huge cosmic iceberg. And here's a fascinating possibility. Some interstellar objects may carry complex organic compounds, perhaps even amino acids, the building blocks of proteins. Comets in our own system contain such molecules, formed through complex chemistry in cold environments. If interstellar comets also contain them, they may have spread the ingredients of life throughout the galaxy. This raises the old idea of panspermia, that life, or at least its chemical components, can be distributed between star systems by comets and asteroids. Perhaps life on Earth was partially seeded by material delivered by interstellar visitors billions of years ago. Perhaps life is, in some sense, a galactic phenomenon rather than a purely local one. Before we continue, pause for a moment. If you are watching or listening to this now, where are you located? Write in the comments. What city, what country are you contemplating these cosmic mysteries with us from? It's comforting to know that people around the world share this curiosity about the universe. Oumuamua, that first detected interstellar visitor, behaved strangely. As it left the solar system, it accelerated in a way that couldn't be explained by solar gravity alone. It was a subtle but definite acceleration, something beyond what we expected. And this raised all sorts of speculation, including, somewhat humorously, theories about alien technology. Could it be an artificial solar sail? a reconnaissance probe from another civilization, many astronomers believe the most likely explanation is natural. Invisible jets of gas being ejected from the surface of Oumuamua as it heated up, acting like small rockets. But this hypothesis has never been definitively confirmed because Oumuamua was already leaving the solar system when it was discovered, so there wasn't enough time to study it in detail. It remains an intriguing mystery. Interstellar objects can reach speeds exceeding 200,000 kilometers per hour relative to the Sun. These extraordinary speeds indicate that they were violently ejected from their home systems. Something dramatic happened to give them enough kinetic energy to escape the gravity of their home star. Ejection can occur through giant planetary collisions, two planets or protoplanets colliding at orbital speeds, fragmenting and launching debris in all directions. Some of these fragments may acquire enough speed to escape the system entirely. Or it can occur through gravitational interaction with large planets, like a Jupiter in another system throwing comets and asteroids onto escape trajectories through close gravitational encounters. It's a process that happens in our own solar system occasionally, ejecting objects into interstellar space. Some interstellar visitors may have even more exotic origins. They could be fragments of dead stars, such as pieces of the crystalline crust of a white dwarf that was destroyed by a supernova explosion or collision with another star. Or stellar material itself, not planetary material wandering through the galaxy. Others may be fragments of icy exoplanets, Pluto or Triton-like worlds in other systems, broken off by impacts or tidal forces and ejected into the interstellar void. And there are even more intriguing speculative possibilities. Perhaps pieces of interstellar moons also exist. Fragments of satellites that orbited giant planets in distant systems, now wandering independently after some catastrophe released them. But finding interstellar objects is extremely rare. We have detected only 3 so far in the entire history of modern astronomy. Not because they are rare in the absolute sense, billions may be out there, but because finding one requires perfect alignment with our telescopes at the right time, with sufficient brightness to be noticed. The chance of spotting one depends on orbital geometry, timing, and pure luck. It's like fishing in a vast ocean with a tiny net. Occasionally, you catch something, but you know there's so much more out there that you'll never see. And that's changing. Several space agencies are planning future missions to intercept interstellar objects. The idea is to have spacecraft waiting in orbit, ready to be quickly redirected when a new visitor is detected, reaching it while it's still within the inner solar system. The European Space Agency is already seriously studying the Comet Interceptor mission, a spacecraft that would orbit at the Lagrange point L2, waiting for a long-period comet or, ideally, an interstellar object to unexpectedly enter the spacecraft. When the target is identified, the spacecraft would be launched on an intercept trajectory, studying the visitor closely as it passes, and some interstellar objects may have extremely thin atmospheres, tenuous envelopes of gas sublimating from their surfaces, invisible to ordinary telescopes but detectable by specialized instruments. Studying these atmospheres could reveal chemical composition in extraordinary detail. Let your mind wander through these possibilities. Fragments of destroyed worlds, seeds of life scattered across the galaxy, dizzying speeds. Relax deeply. More interstellar mysteries await. Some interstellar objects may carry exotic ices, forms of frozen matter that simply do not exist in our solar system. Perhaps chemical combinations that only form under specific conditions around certain types of stars, or in environments with elemental compositions different from our own. Ices that, when heated by the sun, evaporate in unexpected ways, creating unpredictable movements that confound attempts to predict their trajectories. And there are intriguing theories about their origins. Some interstellar visitors may have been born in binary systems, places where two stars orbit each other in an eternal gravitational dance. Binary systems are especially gravitationally chaotic, efficient at ejecting objects into interstellar space through complex three-body encounters. Planets, comets, and asteroids in such systems live precarious existences, constantly disturbed by two massive sources of gravity. And the journey of these objects can be epic beyond imagination. Some may have traveled through hundreds of star systems before reaching ours, passing through molecular clouds, close to other stars, witnessing cosmic landscapes we will never know. They are true travelers, galactic wanderers with stories written on their altered surfaces. Because cosmic radiation, high-energy particles that permeate intergalactic space, can alter their surfaces over millions of years, creating dark, chemically altered crusts. It's like a cosmic patina, an aging process that makes interstellar objects increasingly darker as they drift. Some can become so dark that they reflect less light than coal, objects almost perfectly black against the black background of space. This causes many of them to go completely unnoticed by ground-based telescopes, which rely on reflected light to detect objects. They are invisible ghosts, crossing our system without leaving a trace in our records. Interstellar objects with cometary tails can carry extremely ancient dust, grains that condensed around stars that existed and died long before our sun was born. Dust older than our entire system, preserved in the interstellar cold, now briefly illuminated by the sun before returning to darkness. Spectral analyses of this dust can reveal elements formed in ancient stars that exploded as supernovae eons ago. It's stellar archaeology, studying the remnants of past stellar generations brought to us by interstellar visitors. And the diversity of interstellar objects reflects the diversity of their systems of origin. Rocky objects may have been born in the inner regions of distant planetary systems, close to their stars where temperatures were too high for ice to survive. They are fragments of terrestrial worlds, distant siblings of Earth and Mars. Icy objects, on the other hand, likely came from outer regions, from the Oort clouds of other stars, reservoirs of comets on the boundaries of planetary systems. They are emigrants from icy regions where giant planets never formed, or where objects were gravitationally perturbed into interstellar space. Some visitors may be ghost stones, objects that only become visible when illuminated by the sun, appearing suddenly as they enter the inner system, shining briefly and then disappearing again as they depart. To observers, they seem to materialize from nothing and fade back into nothingness. And perhaps there are cosmic monoliths, metallic fragments created in violent stellar collisions, such as when two white dwarfs collide or when a neutron star rips material from a companion. Fragments of processes so energetic that we can hardly imagine them, now wandering silently through the galaxy. There are even speculative theories, more hopeful than proven, that some interstellar objects could harbor dormant microorganisms, bacteria, or even simpler life forms, protected deep within rock or ice in a state of suspended animation, surviving the vacuum and radiation for eons. If this is true, interstellar objects would be natural capsules of life, spreading organisms throughout the galaxy in a slow but inexorable process of panspermia. And here's a humbling thought. Scientists believe that many interstellar objects may have passed by Earth undetected. Not hundreds, but possibly thousands throughout the history of astronomy. Too small, too dark, or simply not observed by telescopes that were pointed elsewhere at the crucial moment. An impact of an interstellar object on Earth would be extremely rare. The odds are astronomically low, but not impossible. And if it did occur, it would be an extraordinary scientific event. The impact could reveal completely unknown chemical materials, minerals that do not exist in our system, perhaps even signatures of exotic chemistry from radically different planetary environments. Finally, although we detect only a few interstellar objects, the reality is that dozens, perhaps hundreds, likely traverse the solar system every century. But we only detect the largest and brightest, those that happen to pass close enough to the sun to become active, or that are large enough to reflect detectable light. Most remain invisible, known only statistically, not individually. Feel the vastness of this hidden population. Thousands of silent visitors, crossing unnoticed, carrying stories of worlds we will never know. Keep breathing calmly. The journey with the interstellar visitors continues. Some interstellar objects may be so old that they formed even before the Milky Way was fully structured as we know it today. 12 billion years ago, when our galaxy was still forming, accumulating matter, merging with smaller galaxies. Objects may have been born in those primordial times and wandered ever since. Silent witnesses to galactic history. They may be remnants of galaxies that merged with the Milky Way in the distant past. When galaxies collide and merge, a violent process that takes hundreds of millions of years, objects are hurled in all directions. Some of these fragments of extinct galaxies may still be wandering, carrying in their chemical composition signatures of galactic environments that no longer exist. The surface of these older objects can record billions of years of exposure to cosmic radiation, acting as cosmic diaries, where the history of their journey is literally engraved in the atomic structure of their outer layers. Analyzing this radiation alteration can reveal how long the object spent in interstellar space and what types of environments it traversed. And interstellar radiation, high-energy particles, cosmic rays, ultraviolet light from distant stars, can transform their surfaces into glassy materials, creating a kind of space obsidian. Fused and vitrified outer layers due to prolonged exposure to energies that would never naturally exist on planetary surfaces protected by atmospheres, and the size of these visitors varies immensely. Some can be as small as pebbles, traveling through space as cosmic dust, tiny grains that traverse star systems completely undetected, visible only when billions of them collectively form diffuse clouds. Others, theoretically, could be the size of terrestrial mountains, colossal objects kilometers in diameter, completely invisible until they get close enough to the sun for their movements against the stellar background to be noticeable. Imagine a mountain traveling through interstellar space for millions of years, finally crossing our system unnoticed because it was too dark to detect. Interstellar objects can form in multiple ways. When young stars form from collapsing molecular clouds, they often expel excess matter, jets of material that are launched outward by magnetic fields and radiation pressure as the star stabilizes. Each newborn star likely sends billions of fragments into interstellar space as a natural byproduct of its birth. The vast majority of these fragments never encounter another star system. They wander in the void between stars for eons, millions, perhaps billions of years, traversing parsecs of nearly empty space, never again interacting meaningfully with anything. But some, by sheer cosmic chance, find their way to systems like ours. They enter as visitors, their trajectories curved by solar gravity, briefly warmed by starlight for the first time in eons, before departing once more into darkness. And they are, in a way, natural spies of the cosmos. Interstellar objects reveal the raw material of other systems, the chemical composition, the types of ice, the proportions of elements. It's unintentional cosmic intelligence, samples freely given that allow us to compare our system with others without having to travel there. Some may even have weak magnetic fields, not strong fields like planets with molten iron cores, but residual magnetization accumulated along their journey through weak interstellar magnetic fields. When they enter the solar system and interact with solar winds, this could theoretically generate faint auroras, faint and ephemeral glows, almost impossible to detect, but perhaps present. There are theoretical models suggesting that interstellar objects can form clusters, small populations traveling together over long distances. This clustering can occur after they are simultaneously ejected from a multiple star system, where complex gravitational interactions eject multiple objects with similar speeds and directions. They gradually separate over millions of years, but for a time, they travel as a loose swarm through the void. Interstellar objects can collide with each other in deep space. It's extremely rare. Interstellar space is vast, and objects are comparatively tiny, but statistically unavoidable over galactic scales. When two of these cosmic rocks collide far from any star, the collision could fragment them even further, sending small pieces in all directions, creating secondary populations of even smaller fragments. Some resulting fragments can be accelerated to such high speeds that they exceed the escape velocity of any normal star, moving so fast that not even a massive star could gravitationally capture them. These ultra-fast fragments would be nearly impossible to detect with our current instruments. They would cross the solar system in a matter of days or weeks, too fast for detailed observation, and only noticed retrospectively in data analysis. And here's a provocative possibility. There are theories suggesting that advanced civilizations could, in the future, or perhaps already have, launch interstellar probes so small and seemingly natural that they would appear to be ordinary asteroids. Perfect camouflage. An exploratory probe disguised as a space rock, passing through star systems unnoticed, observing silently. This raises the question: how would we distinguish an artificial probe from a natural object? If the technology is advanced enough, the distinction may be impossible without direct inspection. Perhaps some of the interstellar objects we observe are not purely natural. They probably are, but the possibility remains, a reminder that the universe may hold surprises that our imagination is only beginning to explore. Let your mind wander through these possibilities. Cosmic diaries etched on altered surfaces, groups of visitors traveling together, collisions in the deep void. Relax even more deeply. We are approaching the final revelations about the interstellar messengers. If an interstellar object were to collide with Earth, an extremely improbable but not impossible event, it would leave a chemical signature never seen before. The impact site would contain elements in strange proportions, minerals that do not exist naturally in the solar system, compounds formed under conditions radically different from our own. It would be an instantly recognizable geological anomaly, a scientific gift from another star system delivered violently. This impact could reveal completely unknown minerals, crystalline structures that only form under pressures, temperatures, or chemical compositions that simply do not occur in our system. It would be like opening a geological time capsule from another world, frozen at the moment of impact. And some interstellar objects may carry very weak magnetic fields. Not intrinsic fields generated by molten metallic cores, but remnant magnetization, traces of magnetic fields from planets where they once existed. If we could study these fields closely, we could potentially reconstruct properties of the magnetic environments of their parent systems. Each interstellar object carries unique chemical fingerprints from its system of origin. The ratio of isotopes, variance of elements with different numbers of neutrons, is determined by the nuclear processes in the stars that created them. Analyzing these isotopic ratios is like reading a cosmic barcode that identifies what kind of stellar environment the object came from. A space mission designed to intercept one of these objects would be technically challenging and would take decades to plan, build, and execute. We would need spacecraft already positioned, ready to be launched quickly when a suitable target is detected. It would be an expensive and risky undertaking, but it would also be the first real chance to touch, to directly analyze material from another planetary system. Not reflected light observed through telescopes, not spectral inferences, but direct physical analysis, touching, drilling, measuring a piece of another world. It would be a defining moment in the history of astronomy. And some interstellar objects may be so old that they formed before the Milky Way assumed its current spiral shape. 10 or 12 billion years ago, our galaxy was very different, more chaotic, less structured, perhaps still absorbing smaller galaxies. Objects formed in those primordial times could carry dust from pre-galactic eras, material that witnessed the youth of the Milky Way itself. Studying these ancient objects can help us understand how the galaxy evolved over billions of years. They are physical samples from past galactic epochs, preserved by interstellar travel that protected them from recycling processes that alter material within active star systems. And there are provocative hypotheses, not mainstream, but not entirely dismissed either, that advanced civilizations could use interstellar objects as natural probes. The idea is elegantly simple. Why build expensive spacecraft when natural objects have been traveling through space for millions of years? A sufficiently advanced civilization could identify interstellar objects passing through its system, attach a small, discrete instrumentation, and let them continue their journey, now carrying sensors that collect data as they travel. These modified objects would be indistinguishable from natural objects to distant observers. It would be perfect camouflage. And if interstellar objects truly serve as carriers of alien instrumentation, we would never know without extremely close direct inspection. But beyond speculation about alien life, interstellar objects have important terrestrial scientific uses. They can be used as benchmarks to measure the movement of the galaxy itself through the universe. Because they are not gravitationally bound to any star, their trajectories reflect the background galactic motion in a purer form. And they help test models of gravity and stellar dynamics. As more interstellar objects are detected, their accumulated trajectories will provide statistical data on mass distribution in the galaxy, including invisible dark matter that affects their trajectories in ways we can only infer. Future generations, equipped with giant space telescopes and more sensitive detection networks, will be able to track thousands of these objects simultaneously. What is rare today, detecting 3 interstellar objects in all of history, could become routine, with growing catalogs of documented visitors, their orbits tracked, and their properties cataloged. And there are even speculative proposals that some of these objects could be redirected using gravitational propulsion. Carefully planned encounters with planets that alter their trajectories, guiding them into orbits where they can be more easily studied or even temporarily captured in orbit around the Earth or Moon. Every interstellar object is unique. There is no standard or typical one. Each has its own composition, history, and trajectory. Some are rocky, others icy. Some are active, others inert. Some have traveled for millions of years, others for billions. Each is a cosmic individual with its own silent narrative. They are like time capsules, bringing stories of stars that may no longer exist. A star that exploded as a supernova billions of years ago, ejecting material into interstellar space, may have its last physical traces wandering through the galaxy in the form of interstellar objects. They are mobile monuments to extinct worlds and suns. Detecting them is like finding bottles thrown into the cosmic sea. Imagine the ocean of the galaxy, with billions of stars as distant islands, and between them, objects floating through the liquid void of space. Occasionally, one of these bottles crosses our cosmic shore, and if we are lucky, we notice it before it passes. And each of these bottles carries a piece of the galaxy's history, waiting to be deciphered. Unintentional messages written in chemistry and physics, telling us about places we will never visit, about stars we will never see, about worlds that existed and disappeared so long ago that their light has already gone out. Now, take one last deep breath. Let your mind absorb this journey through the visitors from other worlds. We journey from the discovery of 3I Atlas in 2025. Explore the first visitors, Oumuamua and Borisov. Contemplate the dramatic origins of these objects. Fragments of destroyed worlds. Remnants of protoplanetary disks, ejected by collisions or violent gravitational interactions. We learned about their radiation-altered surfaces, their possible tenuous atmospheres, the chance that some might carry organic compounds or even dormant life. We imagined exotic ices that don't exist here, glassy crusts created by eons of cosmic exposure. We contemplate their profound ages, some possibly older than our galaxy in its current form, bearing dust from pre-galactic eras. And we speculate on provocative possibilities, disguised artificial probes, civilizations using natural objects as instrumentation carriers. And we recognize the rarity and preciousness of each detection. 3 confirmed objects in all of human history, but billions likely wandering the galaxy, invisible, unknown. Each detection is a scientific gift, a window into systems we could never otherwise visit. Interstellar objects remind us that the solar system is not isolated. We are part of a dynamic galaxy where material is constantly exchanged between systems, where fragments of distant worlds occasionally cross our path, where we are connected through these silent messengers to stars and planets scattered across hundreds of light years. and they give us hope. That through these visitors, we can touch other worlds without having to travel there. That the galaxy sends us scientific gifts regularly, if only we have the eyes to see them. That we are not alone in the darkness, but connected through a network of traveling objects that link star systems like buoys floating in a cosmic ocean. Sleep well. Dream of visitors from distant stars, of bottles floating on the galactic sea, of messages written in chemistry waiting to be read. Good night.